welcome back to another exciting day working with absolute values. Today we're going to use or solve absolute value inequalities instead of equations, but I want to go through a couple equations just as a review. So now would be a really great time for you to pause the video, work through these two examples that are here, and then restart the video to see if you have the same answers I did. Okay, pause the video now. Here are my answers. And notice this first one, when it equals 0, positive 0, negative 0 don't make much sense, so we have just the one solution, and it checked out. And that second one, I had to add the 20 and divide by 4 before I could separate, and I got two answers right there. Hope you got the same ones. Now let's look at some absolute value inequalities. So we'll have less than, greater than or equal to, less than or equal to, those types of things. When we separate into the two separate things, we are either going to have an and inequality or an or inequality. And here they're called between and beyond. Between just means we're talking about an and, all right? That's highlighted down here. And beyonds are the ors, so when we connect them, they will be or. Now, good things to notice are and inequalities are less than symbols or less than or equal to symbols. So I always say to my Algebra 1 students when we first learn this, we say less than a little bit funny, and it reminds us that we are doing an and inequality. So less than reminds you it's and. Okay? Beyond or the or inequalities, greater than or equal to. So again, if we say it a little bit funny and we say greater, then we remember the greater than ones are or. So that's just a little trick that some students quite a while ago came up with, and I've used it ever since because it was a pretty genius idea. It's how we can remember whether it's and or. Okay, so let's solve some of those. This first one, we're talking about absolute value of 11 minus 2x greater than or equal to 13. So we have an or, which when we're talking about the terminology as between or beyond, or is a beyond because they go in opposite directions, just like the oars on a boat. So, same rules as yesterday. We isolate, we separate, we solve, and we check. And then there's a graphing of the solution as well. So, absolute value in this one is already isolated, so we're ready to separate. And we're going to separate with that magical word or, because this is a greater than inequality. So, 11 minus 2x greater than or equal to 13, or 11 minus 2x. Now we flip that sign, less than or equal to a negative 13. So we're looking for things that are 13 units away on the left and on the right. So that's why we have the sign flipping to negative 13 on that negative side. Okay, so then we solve each like we have been doing. Subtract 11 from both sides. 13 minus 11 is 2. So I get x, almost messed up there, x less than or equal to negative 1, because I have to flip that inequality when I divide by the negative 2, or negative 2x less than or equal to negative 24, and x greater than or equal to 12. So a graph of that, remember how we graph our inequalities on a number line. We're going to have, I need a negative 1 over here and a 12. And graphing above is such an easy way to see it. So I'm going to go ahead and I'm going to have a closed circle here at negative 1 and go off to the left, and a closed circle at 12 and go off to the right. And then of course we can check our work, which is always a really good idea. But now to check it, we don't necessarily use the values that we solved and put on the number line. We want to choose something over here in this solution region. So anything less than -1, and we also want to check something greater than 12. So you can pick whatever you want. I think I tried an x equals -2 because that seemed like a pretty easy number to work with. And when I take 11 minus 2 times -2, I get 11 plus 4. Absolute value of that is 15, which is greater than or equal to 13, so that checks out. And then I think that we should maybe do an x equals 13. So 11 minus 2 times 13, 11 minus 26, that is 15, which is greater than or equal to 13. So they both check out. Okay, super fun, right? Let's try another one. Let's try this x plus 8 less than. So we know that's an and it's a between. Okay, less than is an and. Okay, so same idea. We have the absolute value isolated. Step number 1 is done. Now when you separate it, you can do it one of two ways. You can do x plus 8 less than 5 and x plus 8 greater than -5. Flip the sign and do it that way. Or I like to keep my and inequalities all at once, or all in one. So I write mine like this. I do -5 less than x plus 8 less than 5. Both of these will get you to the right answer. It's kind of personal preference which one you want to use. I'm going to use this second one here because that's my favorite. So subtract 8 from both sides, all three parts actually. And I'm going to have -13 is less than x is less than -3. So a graph of that, -13, -3, open on both, and shaded between. Okay, to check this, again, we only want to choose a number that's inside of the region, shaded region, so we could check something like a -5 if we wanted to. So let's check out -5. -5 plus 8 is the absolute value of 3, and that's 3, which is less than 5. So it all checks out there. Okay, again, if you're more comfortable with this method of writing the and statements, you certainly can do that. I just have a preference for the other one. The last thing we like to talk about with absolute value inequalities is this idea of absolute deviation. And absolute deviation is any sort of ideal amount that you're willing to have a little bit of wiggle room in. Okay, so if we talk about bowling pins, in order to be legal for bowling pins, the weight should be between 50 ounces and 58 ounces. Okay, we can write an absolute value inequality that shows those possible weights. So things to think about when you're going to fill in the pieces of this inequality that we have over here. We want to think about things like what is the perfect weight for a pin and how much are we willing to miss it by. Okay, so X is going to represent the actual weight of a pin. If we pick up a pin and we weigh it, what is it actually going to weigh? That's what X is. And we want that to be within so many units of the ideal weight. So if they can be between 50 and 58, that is an ideal, what's in the middle? 54. So the perfect weight is 54 ounces. And if that's ideal, how much were we willing to miss it by? Well, we went down to 50, so that's 4 ounces, and up to 58, so that's also 4 ounces. So we're willing to miss by 4 ounces. How does that translate into an inequality? Well, if I take the actual weight of a pin and I subtract off the ideal weight of 54 ounces, that difference, the absolute value of the difference, should be less than or equal to 4 if I have legal bowling pins. All right, so your perfect weight goes right inside there with the absolute value, and the amount you're willing to miss by goes right outside. And that is just one application of these absolute value inequalities that we are working with today. Please let me know if you have any questions, and I'd love to help you out. Have a good day.